So today I would like to look at section 3.6. In 3.6, we'll look at implicit differentiation and related rates. In this section, we're going to look at implicit differentiation, which basically is taking the derivative of expressions where it's difficult to isolate the y by itself. So something like this would be a function that's y is defined implicitly as a function of x, meaning it would be very difficult to get that y isolated by itself. So we have kind of an intermingling of the x and y functions together. So for instance, like here, if we have it like written like this, then that's an implicit equation. An explicit equation would be if we actually solved it for the y. And so that's primarily what we've been working with up until now are these explicit equations. But in today's class, we're going to look at some implicit equations and taking the derivative of those. Okay, so our process here in doing this, there's really two steps. We're going to differentiate both sides of the equation with respect to x, and you'll kind of see how that works as we go. So, and then we're going to solve the resulting equation for dy dx, because dy dx does represent the derivative of y with respect to the variable x, and that's what we're going to be looking for here. So if you'll keep in mind, when you're differentiating a term that has y's in it, you're always going to put dy dx beside of that. And when you're differentiating a term with x's, you won't need to do that because the dx, you'll be putting, it would basically be dx with respect to x, which is just going to be 1, and it's not necessary that we write that. Okay, so if we have an example like this, let's say we have y squared equal to x. So this would be, y would be implicitly defined in terms of x. So we don't have y just by itself. We're asked to find the dy dx. So the first thing we're going to do is take the derivative with respect to x of both sides. So when I take the derivative with respect to x of this side, we just want to apply our normal power rule to this. So we would bring the 2 down, we'd have the y, and this would drop to the first power. So we'd have the 2y part. But because we're taking the derivative of y and not the derivative of x, we're going to need to put this dy dx beside of it. And then on this side, when we take the derivative of the x, that's just going to be 1. We don't need to put dx here because that's not necessary. Okay, so we're asked to find dy dx, which is this. And so that means we need to get rid of the 2y. Since these are multiplied together, we're simply going to divide both sides by 2y. So when we divide both sides by 2y, we're going to be left with dy dx by itself here. And we're going to have 1 divided by 2y on this side. Okay, I want to look at a couple examples of this. So the next example we're asked to find dy dx using implicit differentiation. So again, we don't have our equation solved just for y. We have it defined implicitly in terms of the x. So we'll take the derivative of this first term. Okay, basically we're going to take the derivative of both sides. But in doing that, we're going to eventually end up taking the derivative of each term here. So the derivative of 3x squared is simply 6x. No need to put the dx here. And then here we've got the derivative of y squared would be 2y, but we do need to put dy dx because this is a y term and we're taking the derivative of a y term, so we need to follow that with the dy dx. The derivative of the 7 would be 0. And then we're just left to solve for dy dx. So in doing that, we're going to put all the dy dx terms on one side, and all those that do not have dy dx will go on the other side. So we're going to move the 6x over to the right side, and then we're going to divide away the negative 2y. So we end up with this expression, which we can clean up a little bit. 2 negatives make a positive, and then 6 over 2 gives us 3. And then we have the x and the y. So our derivative here is defined in terms still of an x and a y. Okay, here's another one. Again, another implicit differentiation problem. So let's take a look at this one. Um, we're going to take the derivative of both sides with respect to x. So eventually we're going to be taking the derivative of each individual term. So when I take the derivative of y to the third, that's going to be 3y squared. And since it's a y term, I'll follow that by the dy dx. Here, the derivative of y would just be 1, just like the derivative of x is 1. Derivative of y would be 1, and then we'll follow that again by dy dx because it's a y term. Here we've got the derivative would just be 6x squared. We don't put dy dx because this is an expression with x's. Here the derivative of x is just 1, and then here the derivative of 8 is 0. Okay, so we have dy dx's in two different places. So the way to separate those would be to put all the dy dx terms on one side and all those that don't have dy dx, which would be this term and this term, put those on the opposite side. Okay, so if I group the dy dx terms here and the non-dy dx terms over here, and get them separated, then what I can do is I can factor out dy dx from these two terms. So if I take a dy dx out as a GCF, this term it leaves me with 3y squared, and this term it just leaves me with a 1 as a placeholder. And I really don't do anything to this side. Okay, and then I'm still trying to solve for dy dx. So after I have it factored out, I'm going to divide away this part. So I'll divide both sides by the 3y squared minus 1. And so this side, the left side will be left with dy dx, and the right side with 1 minus 6x squared over 3y squared minus 1. Okay, so here's one. We want to work with this equation. This is actually the equation of a circle centered at the origin with a radius of 2. So we want to find dy dx by implicit differentiation, and then find the slope of the tangent line, and then find the actual equation of the tangent line. So looking at this by implicit differentiation, when I take the derivative of this would be 2x. The derivative of this would be 2y dy dx. The derivative of 4 would be 0. Okay, so we're taking the derivative of that. We want to solve for dy dx, so I'm going to move the 2x to the other side and it'll become negative. Then I'm going to divide away the 2y, and I'm left with this. I can reduce the 2's, and so I have negative x over y. So that would be my equation for dy dx. Okay, as far as the slope of the tangent line, we know that the slope of the tangent line is given by the derivative. So I just need to go back to this expression for the derivative and plug in this as my x. So the 1 is my x, and the square root of 3 is my y. So if I plug in 1 for my x and the square root of 3 for my y, then you can see that this is the slope of the tangent line. Okay, the equation of the tangent line itself, we're going to go back to y equals mx plus b. So I'll need m and I'll need b. So I'm given my x and my y, and I just found my m, okay, my derivative. So I'll plug those in. So I'm going to put in the square root of 3 for the y. I'll put this expression in for the m, and then I'll put 1 in for the x, and I'll solve for b. So this gets a little messy. I'll move this term over. So I'll have the square root of 3. It will become a positive when it moves over. I'll have plus 1 divided by the square root of 3 as my b. And so then I'll just write that into the y equals mx plus b. Substitute this in for the m. Substitute this in for the b. And I'll have my equation of the tangent line. Okay, I wanted to show you one that involves the implicit rule with the product rule. Okay, so here looking at this is definitely defined implicitly, and we're asked to find dy dx, so we'll have to do that by implicit differentiation. So if I take the derivative of this, that's pretty straightforward. That's just 2x. But the derivative here is the product of x and y. So I actually have to do a product rule for this part. And the derivative of 6, that's easy because that's just the 0. So this is the part that poses some problems here, where we have to do the product rule. So the 2, it comes out as a constant, so that's not really an issue. It's just the derivative of this x times y. So if I consider the two functions to be x and y, and I do our little box, the derivative of x is 1, the derivative of y is dy dx. Okay, so when I do the product rule says I'll multiply x times dy dx plus y times 1. So we do the cross with the plus. Okay, and that gives me this part in here. Okay, so the 2 was just factored out as a constant. This part comes from the product rule using the box. And then we're just going to like clean it up with the signs. So I'm going to distribute the -2 through this parenthesis. I'm going to isolate the dy dx by itself and move the other terms to the right side. And then I'm going to divide by the -2x. The 2's all would cancel and it would leave me with this expression here for the dy dx. So anytime you have an expression where you do have two things multiplied together using your x's and y's, you would have to implement the product rule at that point. Okay, related rates is the last part of this section. Related rates is implicit differentiation is incorporated into related rates quite a bit. It's a useful technique when solving related rates problems. We could do a lot with related rates, but I'm not going to do a lot. I just want to do a couple problems that involve an equation that's already given to you. So some of these steps that the book outlines for us won't necessarily apply because you're going to be given the equation, so you're not really going to be asked to find an equation that relates the variables. So you're really going to be doing these last two steps, differentiating both sides implicitly, but you're going to do this with respect to t for time. So instead of differentiating with respect to x, you're going to differentiate with respect to t. Then you're going to replace the variables and their derivatives with the numerical data found in your problem and then solve for the required rate of change. Okay. So on this one, we've got a study was prepared for the National Association of Realtors that estimates that the number of housing starts in the Southwest is defined as N of T, where the units are in millions, over the next 5 years is related to the mortgage rate R, and that R is as a percent per year by this equation. Okay, so basically we've got R and N defined implicitly in this problem. It says what is the rate of change of the number of housing starts? Okay, so the rate of change of the number of housing starts is what we're trying to find. We want to find that with respect to time, so we're going to differentiate with respect to t. When the mortgage rate is 11%, and for this problem, since R of t is given as an actual percent, R is going to be 11. I know normally we would convert that. We're not going to do that. We're not going to convert it in this problem. And it's increasing at a rate of 1.5% per year. So again, the 1.5 is going to be given there. Okay, so for this one, we want to find the rate of change of the N of t with respect to time. So basically, we want to find the derivative of n with respect to t. So dn dt is what we're asked to find when it says the rate of change of the number of housing starts. Okay, so first thing, if we take the derivative with respect to time, the derivative here would be 18n. So just multiplying the 9 times the 2 will give me the 18n. Decrease the power by 1, and then we're going to have dn dt because we're taking it with respect to time. Over here, if I take the derivative of r, that's just 1, but I'm going to have dr dt. Okay. And then the derivative over here would just be 0. So when we do related rates, all the variables are going to get these dn dt's and dr dt's because they're going to be in relation to the third variable, time. Okay, so looking at what we've been provided with here, okay, we're told that the mortgage rate is 11% per year and it's increasing at the rate of 1.5% per year. So basically what they're telling us with that is that when the rate is 11, the derivative of the rate, okay, so that's how much the rate is increasing, tells me it's the rate of change of the rate. So dr dt would be 1.5. So we're going to go and plug in what we know. So we know that r is 11 and we know that dr dt is 1.5. Okay, so if I put dr dt in here as 1.5, then I'm going to need to get dn dt by itself. So I'm going to move dr dt, which is 1.5, to the other side, and I get this equation here. So now I'm just solving for dn dt, which means I'll divide by the 18n. So I'm going to have negative 1.5 over 18n. Okay, so in order to actually answer this question, which is what is the rate of change when the mortgage rate is 11% per year, I need to know what the n is that goes with the rate of 11% per year. So I'm going to go back to this original equation here, and I'm going to plug in 11 for the r, and that's going to give me 9n squared plus 11 equals 36, which is what I have here. Okay, I'm going to solve this for n, so I'll subtract 11 from both sides. That'll give me 25, divide by 9, and then to get n by itself, I'll take the square root, which will give me 5 over 3. I don't really need to worry about the negative square root because I wouldn't have a negative number of housing starts. So I'm just looking at the positive square root. Okay, so to finish this up and to answer the question, which it ultimately is, what is the rate of change? We'll have dn dt is this expression here. We just found out that n is 5/3, so I'm going to make that substitution, and I come out with negative 0.05, and that would be the rate of change. So I have negative 5% as the rate of change for the number of housing starts. Okay, last problem here. This was one, a demand equation for a certain brand of two-way headphones is given. X represents the number in thousands of headphones demanded each week when the unit price is so many dollars. How fast is the quantity demanded increasing when the unit price per headphone is 14 and the price is dropping at the rate of 0.15 headphones per week? And then we've got this hint that's provided here. Okay, so looking at this, I've kind of outlined some things here. What are we finding? We're finding how fast the quantity demanded is increasing. Okay, well, X is representing the quantity demanded. So if we need to find out how fast that's changing, then that's going to be dx dt. We need to find out what dx dt is. Okay, and then it tells us when. So when the unit price per headphone is 14. Okay, so our price is 14. So P is 14. We're also told the price is dropping. Okay, so that's telling me how it's changing. So it's changing at a rate of 0.15 or 15 cents per headphone per week. This would be negative because it's dropping and it's decreasing, so that indicates a negative direction. Okay. All right, so we're going to go back up to this equation and we're going to take the derivative with respect to time. So we'll have 100 derivative of 2x, of x squared is 2x, follow that by dx dt. Plus, then we've got 9 times the derivative of p squared, which is 2p dp dt. And then the derivative of 3600 is 0. Okay, so we're trying to find dx dt. So somewhere we must be able to find x, p, and dp dt. Okay, and that's where the hint comes in. The hint says to find the value of x when p equals 14, solve this equation for X when P is 14. Okay, so I'm going to plug in 14 for P and just solve this. So it actually comes out to be a decimal answer, and this should be approximately equal to this, not exactly equal. I was having trouble finding the symbol on my computer for approximately for that. Okay, so here, going back to our derivative expression, we're just going to plug in the numbers that we know. So we've got 200. We'll put x that we solved for here. We're trying to find dx dt plus 18. The p is the price, which is the 14. And then dp dt, if we go back, we had just said that dp dt is negative 0.15. Okay, so I'm going to put negative 0.15 in here. And so now we really just have all numbers except dx dt. So we'll simplify this, and that will be negative 37.8. When I move it over, it'll become a positive. These, when multiplied, give me 856.9714. Divide both sides by that, and it gives me this number, which is in thousands per week. Which if I have 0.0441 thousand, then if I multiply that by 1,000, that's equivalent to saying 44 per week. So 44 per week, 44 headphones per week is how fast the quantity demanded is increasing when we have a unit price of $14. So if we're charging $14, we are seeing an increase of in demand or in the units of $44, 44 units per week. Okay, if you have any questions, feel free to email me, and I hope to be back on campus and see you soon.